All right, welcome back. So today we're going to focus on the second half of Unit 2, Day 3, which is the complex number portion of our imaginary numbers notes. So if you just see, if I scroll back up, these are the notes we took last. And this is where we are here in complex numbers. So complex numbers are numbers in the form of A plus BI. A and B are going to be real numbers. A is the real part, and then BI is the imaginary part. So pretty much your whole lives, we've been working with the A part. And then this past note sheet, we learned about the BI part. And actually, if we stick them together, we have the whole part. So let me just give you a quick showdown of what that means. Again, so A plus BI. This part is imaginary. This part is real. And together, it is complex. So let's put that onto a chart. I know earlier this year you did your real number system, but now I'm going to tell you that that is only this piece right here, real. The whole thing is our complex number system. And our right side will be our imaginary number system. So think back to the beginning of the year when we did sets of real numbers, and we had rational numbers, and we had irrational numbers like pi. Then we had integers like number 4. We had whole numbers like 0, and we had natural numbers like the number 6. So all of those things are real. On the imaginary side are the things that we worked with together last class. 3i. 0i, that's a big one. We use that one a lot. I'm going to put a box around it. 1/2 I, 0.2i, 86i, right? We could have anything. We could have pi I. Any number that we had real, we can make imaginary by sticking an I on at the end of it, okay? And so within that complex number system, we have all sorts of numbers. We have 3 plus 2i. We have 8 minus 6i. We have negative 1/3 plus 4i. But the key here is that when we call it complex, even though both 0.2i and 0.2 are numbers within themselves, they're both technically complex. We like to think of them as a raw real or a raw imaginary, not just a complex number. And that's because when you think of 0i or you think of 0, how important those are. When I played volleyball and softball, I was the number 13. So on the back of my jersey, there was always the number 13. It would look really silly if we called all numbers by their real name, which would be technically 13 plus 0i. That would just be insane if we write it there. Same reason why if it was 13.00. Those zeros are just placeholders, so that is also equal to 13, but you would just never put them there because there's no need for that placeholder. There's no need to get that information. 13 on its own is more telling. So even though we work with real numbers so often, know that every real number has its imaginary part, and then its imaginary part is just 0. Same with I. So maybe if I had the number 13i, then there was a 0 part in front of it. It has a real part. It is a complex number, 0 plus 13i. It's just kind of exhausting to write it there. So if it's a true complex number and you want to, and it has both a real part and an imaginary part, you need to make sure that you include both. But for simplicity's sake, if it just has the real and the imaginary part is 0i, or if it's just imaginary and the real part is 0, you don't write it. Okay, so we need to be able to simplify expressions. So here they want us to find values of x and y that are going to make each equation true. So let me zoom in on this problem here, and let's talk about what it wants us to do. 4x plus 1 plus 10i is equal to 2 minus 4yi. What color did I do my reals in? My real part I had done in purple. This is my real part, and this is my real part. So 4x plus 1 has to be equal to 2. So if 4x equals 1, then x equals 1/4. Then I have my imaginary part. My imaginary part is 10i, and so is negative 4yi. 10i equals negative 4yi. So I can divide by negative 4i, just like I can divide 10 by negative 4. I can do this division here. And my i's are going to cancel, and I'm going to get negative 5/2 is equal to y. So my solution here, by being able to tell the difference between a real part and an imaginary part, that's so important. I'll show that to you again just so you can see it. So again, I have an imaginary part, which I'm calling this yi, and negative 12i. If yi equals negative 12i, divide both sides by I, then y equals negative 12. That means that 9x minus 5 must be equal to 4. So 9x equals 9 and x equals 1. The imaginary part, especially in the left-hand side where that 5 is separated, the imaginary part is only the part that's attached to the I. The rest is all going to be real. So that's just one thing we can do now that we know complex numbers. Another thing that we can do now that we know complex numbers is learn to add and subtract them. And just like before, I want you to think that you add reals to reals and imaginaries to imaginaries. So I'm going to underline all the parts here that are real, and I'm going to combine like terms. 4 and negative 6 are negative 4. Let's do our imaginary part. I think I've been doing that in blue. 2i and negative 7i is negative 5i. And that's done. That's all we can do here. But it's just taking a long string of numbers, just like simplifying anything, taking something longer and making it a little shorter and making it a little more condensed. And I want to show you here that negatives don't change anything. I always suggest that anytime you have negatives in parentheses, to go through and rewrite it with that negative sign distributed. So this is the same thing as 3i plus 2 minus I. I distributed that negative sign. Now I can go through and do my real part with my real part, and I only have one real part, and then I can do my negative part, my imaginary parts. 3i minus I is 2i, and we're perfect just like that. So adding and subtracting with complex numbers and solving for x and y with complex numbers is really just, can you determine which parts are real, any part without an I, and which parts are imaginary, any part with an I, and your answer will be a complex number. The last little bit here that I want to talk about is dividing complex numbers. So we've already done division with square roots, and that is going to be kind of your key here, is that we need to rationalize, because if a square root is, if I is just a square root of a negative 1, we can't have I in a denominator because we can't have a square root in the denominator. So we want to get rid of it. The good news is it's not so hard to get rid of as long as we know our rules to rationalizing. So you want to multiply the numerator and denominator by I when the denominator is an imaginary number. So that's what we're going to do in example 15. And then I'll show you how in example 16 we multiply by a complex conjugate, which I'll mention in a second. So here's our problem, and it's telling us we can just multiply by by 1, right? I over I. And the reason that this works is that this is going to give me 5i squared in the denominator. Well, what's I squared? What did we talk about last class? Is that we can replace I squared with negative 1, which means that's going to give me negative 5 in the denominator. And we love negative 5 in the denominator because there's no radicals, there's no rational exponents, and there's no I, so it's nice and clean. And then up top, we just have to make sure we multiply. So up top, I have 3i plus 10i squared, which is 3i minus 10, because remember, this is the same thing as negative 1. And so my solution is going to then be negative 10 plus 3i over negative 5. And I'm going to be a stickler here for you guys. Negative on the top, negative on the bottom. We want to get rid of that so we can do the whole thing by changing all of our signs. So the answer is going to be 10 minus 3i all over a positive 5. Okay, let's walk through that one more time. When you have an I in the denominator, you want to multiply top and bottom by I. When you do that, you get I squared. I squared can be replaced with a negative 1, and that's how we got our negative 5. Up on top, we had to distribute. So I got 3i plus 10i squared. Once again, I squared can be replaced with a negative 1, which is how I got 3i minus 10, and then I just simplified to get 10 minus 3i. That works every time, and you're going to have a bunch of practice problems with that. The other thing it can do is just go one step further. We can't do the same thing here. If I were to multiply top and bottom right now by I would get 4i minus I squared, which would give me 4i plus 1, but I'd still have I in my answer, so that is no good. So let me go through and erase this. So instead, we need to multiply by the complex conjugate, which if it's a plus bi is going to be a minus bi. Just like with our radicals and rational exponents, it's just the same expression, just with the opposite sign. So we're going to multiply by 4 plus I. 4 plus I on top and on bottom. Let me show you why this works. 4 times 4 is 16. 4 times I is 4i, but negative I times 4 is negative 4i. And guess what? Those cancel. All that's left is negative I times I, which is negative I squared. We always want to replace I squared with negative 1. So 16 minus negative 1 is 16 plus 1, which is 17 for my denominator. Let's move across the top. Make sure that you FOIL. 2 times 4 is 8. 2 times I is 2i. 8i times 4 is 32i. And 8i times I is 8i squared. So we have a little simplifying to do. I have 8 plus 34i, and 8i squared is minus 8. So I actually am left with 34i in my numerator. And always try to simplify if you can. 34 divided by 17 is 2, and my I doesn't go away, so my answer here is 2i. Let's go through that again. And let me re-explain what I did. We had to multiply by the complex conjugate. It's called complex because it's a complex number, 4 plus I. 4 is the real part, I is the imaginary part. Then we FOILed. Our middle terms cancel, and I'm left with 16 minus I squared. But I squared is the same thing as negative 1. So that's what gave me my denominator of 17 once I got rid of that power of I. In the numerator, I FOILed. I simplified, and I got 34i. And then you always want to check your final answer to make sure that that can't be further simplified. And in this case, it could. So again, keep practicing with that. And we'll check back in and see how you did. That is complex numbers in a nutshell.